Tomorrow.
Tuesday, I like it.
No, let's do a week from today. Another Monday, which would be, no, maybe it's Wednesday. I think it's the 7th,
Monday.
which is Monday. Oh, yeah, it's Monday. Today's the 31st, right? Okay. For some reason, I thought we had another day. Okay. So, yeah, we'll walk through that a little bit. So, on Friday, we kind of got to this point where we had started grasping this idea of shape functions and what do they do for us. Why do we rearrange them as such, right? It's this idea that we're trying to, in the finite element analysis method, right? We're dividing up whatever we're deciding to analyze into discrete sections or elements, right? We need to figure out what the nodal values are, which we're gonna get to next in the class. But once we have those nodal values, we need to be able to have a method to take those nodal values and then figure out what is going on at any point between nodal values in our elements, right? And so that's where shape functions come into play, because it's essentially the displacement, right, or in whatever our field variable interpolation function is, based on what is our known nodal values, right, across that element. So it might be displacement, it might be temperature, it might be snow depth, as you'll find in our homework, okay? So if you plot these, it did in MATLAB, right? Essentially establishes how it flows, right? N1, which is our first shape function, which is a function of, right, multiplied by our first nodal degree of freedom, is really establishing how close are we to that first node. And if we're at the first node, obviously that first shape function is going to dominate the behavior. If we're at the second node, then our second node shape function is going to dominate the behavior. If we add our shape functions together, right, we got to have this 100% contribution or this unity contribution across the entire element. Okay?
What would be the horizontal axis on that graph?
That would be our space variable.
Space variable.
Right, it's like where are we with respect, are we at the beginning, that's why I just did 0 to 1, because it's like, are we at the beginning of our element or at the end of the element? But that could be like, you could be, well, we'll look through the example here in a second, but you could be like in Bozeman, and then you could look at, say, Helena, or something like that. Okay. So this example, say we know the temp in Glasgow and Fairfield, okay? Great places in Montana, right? And we know that Glasgow is 10 degrees below 0 and Fairfield's 15 degrees above, right? The distance between the two is 252 miles, and I'm headed to Lodgepole to compete against Dawson in a fishing derby, okay? And I want to know the temperature, right? So, I mean, this is obviously not structural engineering, but it just shows the applicability of the finite element method to any sort of problem, right? Okay, so we would need to establish, one is like, besides you two, right? Or Jacques, you were from Glasgow, right?
Yeah.
And then Dawson was from Fairfield, okay? Besides you two, what do you guys think the population of Glasgow is? Just a side little tidbit.
10,000?
Jesus, man. We're talking like middle of nowhere, eastern Montana.
Like
1,500.
750?
3202. It's a metropolis out there. Give you guys a scale of where Dawson grew up. What do you think the population of Fairfield is?
1,500.
Man, you are thinking it's a big city. About half that. 607. At least that's what Google told me. I don't know.
Yeah, I'd say that's like pretty close for in town.
Around 600.
Yeah, if you count all the farmers, like maybe 1,000.
Oh, okay. Yeah, push it out a little bit. Try and make it look bigger than you are. Sweet. Okay, so we got Glasgow and Fairfield. We know the temperatures of those 2 points, right? We could devise an element, right, that bridges the gap between Fairfield and Glasgow so that we can figure out where Lodgepole's at, right? In this if we were to plot what was going on, right? If you were gonna say the x-axis, right, we know miles between them, right? We know temperature. What would you call the x-axis? What would that be our variable-wise, right? We have two choices.
Miles?
Yeah, miles, but we would call that our space variable, right? Y-axis, right, so we call this space, which as you mentioned, we're gonna use distance. We know the distance between those 2 points. And then y-axis, right, you might say that this would be our field variable, right? This is what we really want to know. We would call that our temperature. Right, this is our phi sub x, right, that we just went through. It's our field variable. Y-axis, field. So if we plotted our 2 points, welcome, Aaron.
Morning.
Welcome.
It's a blizzard outside.
I really, I haven't seen any snow falling right
Not
now.
anymore.
Okay, okay.
It stopped.
Perfect. Perfect. Okay, let's plot our 2 points. Well, if we had y-axis as temperature, x-axis as our space variable or our distance, right? We knew that Glasgow was 15 below. I might put Glasgow right here. Glasgow. And Fairfield would be somewhere above our x-axis, right? It'd be something like this. This would be Fairfield. Like we did above, right? We have a 2 degree of freedom element, right? We've got 1 degree of freedom at Glasgow, right, the temperature. And we have 1 degree of freedom at Fairfield, which is the temperature, right? And then we have this spatial variable. And so if we have those, we could essentially go up above, right, and steal out our shape functions that we derived, right? We have the same generalized degrees of freedom, right? We've got 2. We put n equal to 1 into here, we get a naught and a1, right? It'd be a naught plus a1 times x. That would be our displacement function, right? Or our temperature function in this case, with respect to our space variable. So I've already solved it. If you guys remember from up above, we get this. Field variable expression or interpolation function with respect to the nodal values.
It's gonna be like X minus, oh, never mind.
Elias, what is it? Huh?
Thought, yeah.
What's wrong? Is it
I
good?
thought that, yeah, I'm good now.
Okay. Right, so we get this interpolation function, right, with respect to our known space variable and our field variable at given locations, right? Phi prime or phi 1, phi 2, x1, x2, and with respect to our field variable or our space variable at our point of interest, right? X. And that gives us our interpolation function. Well, we need to figure out. Anybody have any idea along that yellow line where the lodgepole's at? This is what we effectively did, right? If we were to plot that on the real world, we've got Fairfield way over here, shut up. Right? We've got Glasgow way over here. Tell me when to stop.
Stop.
God, he's good, isn't he? It is right here. What are these mountains called? You know?
Bear
Paws?
The what?
Is it bear paws?
I think these are the bear paws.
I don't
I don't remember either. You guys get a little education on Montana here, right? So Fairfield, or Lodgepole, somewhere out in there, okay? Well, if we were using this interpolation function, right, we need to know our known nodal values, both of our space variable as well as our field variable. And then we need to know our location along this element of where we're at, right? So we've got this space variable, for x. Wow, you guys can't really see that with the shit, can you? But that's all right. So we got our known nodal values, x1, right? 0. We're going to put that at 0. We're going to say x2 is 252 miles. X in our case, well, that x lodgepole to Glasgow, if you were to take an airplane, would be 89 miles. And we know what our nodal values are, phi1 and phi2. So we can figure out what the temperature in lodgepole is. It's negative 1.2 degrees Fahrenheit, right? Obviously, this is a super, super simple example, right? You could have just done this on the calculator by linearly interpolating. It's essentially the same thing. Right? But it's going to get a little more complicated as you start adding in additional variables, or additional, well, either space variables or degrees of freedom. So, what does this look like in a plotted form? Well, these are our quantities. The yellow line is our second shape function times our second nodal value. Red line is our first shape function times our first nodal value. And that blue line is the temperature between them, right? So we get this nice plot, essentially at Glasgow, right? N2 becomes 0, right? Because we zero out. At our Fairfield location, right? N1, our first shape function goes to 0. So this quantity goes to 0. And then it's somewhere in the middle. We can figure out any temperature between the two. Would you guys feel comfortable doing this? No, I mean like in the real world, if you're like, I'm gonna go drinking with Dawson out in Lodgepole, and I really only know the temperature in Glasgow and Fairfield, right? You wouldn't calculate the temperature this way, right?
No.
We need more points, right? So that's where discretization comes into play, right? There's a huge error. The chances that it's negative 1.2 degrees in Lodgepole because Glasgow's 10 below and Fairfield's 15 above, right? Or, yeah, 15 above, right? Very, very slim, right? So we need to make sure that our elements are small enough that we take into account maybe the potential for other, right, nodal values around our point of interest.
You also take elevation into account and do like a line that's not just straight, but like kind of angled at the elevation of each of those.
Yeah, for sure. You can do what we call multiple space variables, right? So that's what we're going to talk about next. Elias, way to go. It's almost like I planted you. Right? What if your field variable varied in 2 dimensions, right? We start giving it 2 dimensions in space. Right? One thing would be, well, obviously, Glasgow and Fairfield have coordinates on planet Earth, right? We'd call those latitude and longitude. Right? So we could figure out, okay, well, now it varies in both latitude and longitude, which might make more sense instead of just distance between them, okay? As Elias said, you might consider elevation, right? That might be a third spatial variable, right? If you guys, has any of you guys used the snow load finder, right? It takes coordinates and elevation into account, right? So you end up getting additional contributions, right? Which hopefully will hone in. Also, right, the element, like if you saw the printout, right, it shows a triangle, something like this, right? Where your spatial the point of interest is somewhere in the middle. And so each one of the element, right, it creates an element, a finite element, around your point of interest if you do the snow load finder, right? And each one of these elements has a coordinate of latitude and longitude and elevation. And in that case also a known design snow load. And so from that, right, we're going to try and figure out our design snow load. So in that case, right, we've got with respect to our, we're looking at the snow load finder. We've got, right, we've got latitude, we've got longitude, we've got elevation. Right, this is spatial values, space values. And we're really just trying to find 1 degree of freedom though, right? Out of that. Snow. Load, or our ground snow load. So for each of these problems that we consider, right, we need to start by considering, so in this case, if we had 3 points, right, and 3 known nodal values, in this case, maybe it's the snow load. Out of these, right, we would have 3 generalized degrees of freedom. So we've got 3 nodal values. In that case, n equals 2, right, from above. Well, don't write that down. Don't do that. Don't do that. That's going to confuse you. Right, so we have A naught, if we looked at our generalized degrees of freedom, right? A naught, A1, and A2. And those generalized degrees of freedom are attached to, right, functions of our interpolation function, right? So we've got A naught, A1, and A2, right? And in the case of having one spatial variable, x, right? If we look from before, right, we had this function right here, right? A sub I, x sub I, right? This is a line element with n nodes. Which essentially means we have one spatial variable, x. So as we continue to add generalized degrees of freedom, our x goes to additional powers, right? It becomes a higher order polynomial as we add additional elements. In this case, though, right, we don't have just x. We might have something of 2 spatial variables. Well, we're stuck with these 3 generalized degrees of freedom, right? So we only get 3 terms to express in terms of our spatial variables, right? Well, the first one, well, the way in which we do this with respect to 2 variables is look at what's called Pascal's triangle. Okay? Pascal's triangle is a depiction of a polynomial to the nth power, essentially 1 plus x times 1 plus y to the nth power. What's that?
Forgot about that.
Oh, good. Glad it came back so quickly. At least you remembered that you saw it. Right? So we want to be selecting lower order terms first, right? And we only have 3 selections in this case, right? Because we only have an element that has 3 degrees of freedom. At the very top of this Pascal's triangle is unity. 1. It's constant, right? So out of these, we get to pick 3. Which ones would you pick?
X to the 4.
Aaron, what's this say right here?
Lower order.
Just ask me which ones I wanted.
What's that?
Just ask which ones we wanted.
Yeah.
A cubed one.
That's just blowing all the way X to the fourth. You barely see it on the screen here. Look at that here. Lower order terms. I'll give you one of them. Wow, there's one, right? That's about as low as it gets. Then X. Then Y. Boom. That easy. So what does that mean? Well, if we were to come up with a interpolation function with respect to X and Y, we would get A naught, right? Times 1, a constant, plus A1 X, plus A2 Y, right? What does that mean for, well, why do we select the lower order terms? Well, it has to do with convergence. Right? Linear terms or lower order terms have more significance in our interpolation function, right? Than say Aaron's X to the fourth. Right? So you can imagine if you wanted something that had a lot higher order of magnitude, you'd have to have a lot more generalized degrees of freedom, which means we need a lot more degrees of freedom in order to do that. Okay. So with that, as I mentioned, and Elias determined that our due date is next Monday. Oh, let's do this. This is the homework, okay? There's a couple problems out of Cook's book here, okay? First problem, we've got 4 3-nodal elements, right? And they want us to come up with essentially this F1, F2, F3. So we want to know what the shape functions are based on knowing, right, these spatial coordinates for each of our known nodal values, right? Very simple, we just establish F1, F2, F3 based on our, right, in this case, it'd be very helpful maybe to do MATLAB or Maple or something like that, because there's matrix math that you could utilize to just do this quickly instead of doing it by hand, right? You can brute force it though, you can do it by hand, right? Next we have this element that's on the bottom left. This is a quadrilateral element, right? It's got 4 degrees of freedom, right? Essentially our field variable at our 4 nodes. So we get A1, A2, A3, A4. You can see how they went down our Pascal's triangle, right? Lower order terms, Aaron. Okay. X, Y, and then X, Y. And they want to know, well, how does our space or our field variable vary with respect to X or Y along each of these sides? And finally, do you think this element will be compatible with neighboring elements that may be attached to it? Any idea what that would mean, compatible? Did you guys see some of that in the homework that's due today? Right. Compatibility is, right, the connectivity or the behavior of our field variable between elements, right? Not at nodes. Nodes, we know that there's compatibility between nodes, right? If an element is next to another element and they share the same nodes, then we have to impose, right, compatibility between them. But if you saw in your VA model sometimes, right, if you had different elements that were attached next to each other like we did in our case study at the beginning of the class, right, a beam element that extends, a beam element say that extended along the side of a plate element, right? These guys would not be compatible, right? Their interpolation functions are different. They're based on different degrees of freedom. And so they're not going to, 1, know each other are there, but 2, they're not going to displace the same way, right? So essentially, we don't want any gaps. So in order for there not to be any gaps right here, between, say, if we did two plates next to each other, I'll leave it to you guys to think about what conditions, right, or what things tell you that this line will be the same between the two.
Don't we need values of B at each of those nodes, like, would we say like B1, B2?
No.
No?
No.
See how B are variable?
No. We're given our field variable, like our interpolation function, right, with respect to the field variable. With respect to x and y, we have this that has known behavior across edges in x and y, right? Last problem. Okay. We know snow depths at 6 locations in the state of Montana. Now I want you to come up with your own interpolation function or method to find the snow depth in Helena. Okay? You can go about this a lot of different ways. All right? Yes, Aaron.
We use Montana ground snow load finder. That's one way.
But see, that is only giving you the design ground snow load, right? That has nothing to do with actual snow depths.
We ratio it based off of the.
It needs to look very similar to the example we did and the notes that we've done with respect to figuring out an interpolation function, right, which has generalized degrees of freedom, okay? And then from that, you can figure out a shape function, interpolation function, right, with respect to known nodal values. Right? It's like you're gonna come up with your interpolation method so you can find the snow depth in Helena. Right? Based on that method you selected, right? Which city has the largest impact on the snow depth in Helena, right? Based on this calculation, you can figure out that, right? Figure that out. What is the field variable in this problem? That'll be easy. It's a field variable. What are we looking for? What do we want? What is or are the space variables in your interpolation, right? There's a lot of potential variables that you could select in order to establish what's going on in Bozeman versus Missoula and Great Falls, and then eventually Helena. As we just mentioned, we've got latitude, longitude, we've got distance, we've got elevation, we've got all sorts of stuff. Okay. Space variable just essentially classifies a known point based on where it sits in space, and that space can be different things. Okay. How many generalized degrees of freedom are there? Okay. It's a function of your nodal values, right? What are your nodal degrees of freedom? There's the physical meaning of the shape functions in this problem. You're going to figure out what the shape functions are. Answer multiple parts of this problem. What geometric entity is described by your interpolation function? Okay. If you use MATLAB or Maple, which would be very easy, or help you, I guess. I wouldn't say easy, but it's going to help you. Right? Just be sure to include your code, just a printout of your code and your outputs. Okay. Any questions? Man, we made it halfway today. That's it. That's all I have for you. We're going to start with mechanics-based element formulations on Wednesday. Okay. Don't forget to get your homework to me today at some point. If I'm not in my office, just slide under the door or between the two doors. I got a Dutch door in my office, okay? Okay.
I haven't watched the lecture on Friday yet, but I got the notes.
What's that?
So I was gone Friday.
Yeah.
Just watched the lecture. I got the notes.